Hello, my name is Craig Belgrad, and this is the Test 2 Rapper video. Now, the point of Test Rapper videos is for the presenter to go through a problem that might have given some people trouble, and the presenter has to work through the problem and make sure it's all correct, so this video can be used for study aid for anyone who wants to learn how to do this problem correctly. So the problem I chose for the last test was problem 4. That gave me a little bit of trouble, but I've solved it completely, and it is ready to become a study aid to help those in need. So here's the problem statement. You put a thin metal pot containing 2 kilograms of room temperature or 12 degrees Celsius water on a hot electric stove. You also stir the water vigorously with an electric beater, which does 100 joules of work on the water every second. You observe that after 15 minutes, the water reaches a temperature of 100 degrees Celsius. The specific heat capacity of water is 4.2 joules per gram degree Celsius. So the first part of this question is, what was the change in E thermal of the water? So the equation you want to use for E thermal is mc delta T. M is the mass of whatever you're putting into the system. C is the specific heat capacity, which is the 4.2 joules per kilogram degree Celsius of the water, and then the change in temperature. So you look back at your problem statement. So the mass is 2 kilograms. Your specific heat capacity is 4.2 joules per gram degree Celsius. And then you have to look at your temperature difference. So the final temperature is 100 degrees Celsius, and the initial temperature is 12 degrees Celsius. So there's your final and there's your initial. That's why I have them underlined. So you go through and you plug in your numbers, but then you develop a problem because you have kilograms for your mass and grams for your specific heat. So you're going to need to change one of these units. So I guess the most convenient way to do that would be to change the 2 kilograms to 2,000 grams. If you were to change this, the 4.2 joules per gram degree Celsius, you could change that into terms of kilograms, but then you'd get numbers that were slightly different, and you might end up getting kilojoules, but we just want joules in this problem, which is the units of energy. So you plug in all your values, and then you want to make sure your units cancel, right? So the grams cancel with that grams, and the degrees Celsius cancels with this degree Celsius. So your temperature change would be 88 degrees Celsius. And then after multiplying, you get your change in thermal energy, which is 739,200 joules. So, and then we move on to the second problem statement. What was the thermal transfer of energy Q into the water from the surroundings? So, you have your change in thermal energy, which is work plus Q. So the total energy in the system is E thermal. Technically, the proper equation would be delta E equals the work plus Q, which is the heat transfer. But since the only energy in this problem is thermal energy, you have to use that. So then your proper equation, after doing some algebraic manipulation, Q is equal to the E thermal minus work. So you have your E thermal, but you're missing your work. Well, they kind of give you hints of that in the actual problem. So you have your 100 joules right here, and it does work on that every second. So the power, you have to use power here. So 100 joules per second equals 100 watts. So that's the power. But if you multiply that by the actual time the power is working, then you get work. And it says 15 minutes. So then you multiply your 100 watts by 15 minutes, but you have to change the minutes into seconds, so obviously you have to do the unit conversions. So the total work from the electric beater done on the system is 90,000 joules. So then you have all the parts of your equation, so you find the heat transfer as 649,200 joules. So then you move on to the third question. What was the change in E surroundings? Well, you're only given one type of energy, which is E thermal. And since you're putting energy into the system, that change in energy is going to be positive. So you're taking energy out of the surroundings. So then you get so your system is your pot and your water. Your surroundings is everything else. So the change in energy for the system is equal to the negative energy change in the surroundings. So in this case, that would become negative E thermal equals E surroundings. So your change in energy in the surroundings is negative 739,200 joules. Because you're adding this much energy into the system, which means you're taking this much energy out of it. So that's why you have the negative sign in front of there. So the last problem statement is you take the pot off the stove and drop 2.26 kilograms of sweet potatoes into the pot. The potatoes are initially at room temperature, which is 25 degrees Celsius, and have a specific heat capacity of 3.14 joules per grams degrees Celsius. Determine the final temperature of the water in sweet potatoes once they come to equilibrium. You can assume that the pot is a very good insulator and does not change temperature, i.e. ignore the change in thermal energy of the pot. So you're given the hint that it's a closed system. So the total energy transfer would be 0. So you have to algebraically manipulate that. So the change in energy of the water is equal to negative the energy change of the potatoes. So you have your typical energy equations, which is mc delta T for both sides of the equations. And then once it comes to equilibrium, you have to find their final temperature. So you have this. So you have all these numbers. Well, I'll walk you through these numbers, okay? So you have, from the previous problem statement, you have 2 kilograms of water. And you have the specific heat capacity of water. But you're not given the final temperature. But you can algebraically manipulate both sides because they're the same temperature. So you just have to factor, well, not factor, you just have to get all your like terms on one side of the equation and constants on the other. And then again, you run into unit complications. You have the kilograms, so you have to change these to grams. So that's what I've done here. And then once you get, and you also want to show your units are consistent. So after all this, you get 8,360 joules per degree Celsius equals the quantity TF minus 100 degrees Celsius. And on the right side, you get negative. You have to have that negative sign still there. 7,096.4 joules per degree Celsius equals TF minus 25 degrees. So then you have to distribute like terms. So then that TF becomes part of this quantity. And then you have your energy right here. And the same thing for this side. So then you get all your like terms on one side of the equal side, and then you get your constant on the other. And then you divide this quantity by this number to get your final temperature. And then your final temperature ends up being 65.57 degrees. So how you could, one way you can kind of think about this problem as a whole is that the water is decreasing in temperature, right? The final temperature is going to be less than the initial temperature. So if anything, this would be a negative sign here. And here in this quantity, the final temperature is going to be greater than the initial temperature, which counteracts, which leaves this negative sign here. So these negative signs eventually just cancel out, and you get something like this. So that's precisely why you end up getting a positive instead of a negative. Some people I've seen said, "Oh, I got a negative temperature." Well, that's not always the case. You never get a negative well, I mean, theoretically, you could get a negative temperature, but in this problem, you shouldn't. So you have to realize this is a closed system. There's going to be no energy transfer to the surroundings, so that's why you have that 0 term up here. So you just have to algebraically manipulate, and that's why I have that minus sign here. This minus sign is just to compensate for the sign. So the negative signs eventually cancel, and then you get your final temperature right there. So this is the step. This is the solution guide to the whole problem. I hope for those of you who use this, it helps. You know, I certainly me doing these test wrappers helps me get a better understanding of the problems I need for, let's say, the final exam. Is we could possibly have a problem like this in our final. But for those who choose to watch these videos, I'm glad I could help, and I hope we all do very well in the final, and I wish you all very good luck.